Okay, welcome. That's very sad. Okay, so structures. Structures. So this is a basic rocket. Our rockets will not look like this. This is made from the guy who taught me rocketry. This slide is probably 4 years old, but here's a rocket. You got your nose cone, airframes, and fins. Probably won't have two sets of fins. This is for a dual stage rocket. This is not what we will be launching for the foreseeable future, but those are your basic components of the exterior of a rocket. So if you start from the back of a rocket, this is the aft. If you remember for flight dynamics, we talked a little bit about the design of a rocket, about how different types of fins configurations can influence the performance. So this is a set of 3 fins on a rocket. You have your fins, then you have your centering rings, motor tube, and thrust plate. So if you remember from last week, fins are needed on a rocket to provide stability. They influence the center of pressure. Motor tube is what contains the motor. It's what contains the motor casing. Motor casing is what contains the actual motor. So there's a series of steps of what holds the actual motor. The motor goes inside a motor casing. If there are 2 types of motors you can launch, there are reusable motors and there are single-use motors. Reusable motors, when you buy them, they are literally a grain that you just ignite. So that grain that you ignite needs to be funneled somewhere. So you put that in a motor case. When you buy single-use motors, it comes preloaded inside the casing, which you just throw away afterwards. But both of these methods, when you purchase them, they will fit inside a motor tube. We generally buy our motors from Aerotech. Aerotech is a specific motor manufacturer, and they make motors to standard sizes. So your standard sizes are 38 millimeters, 54 millimeters, 75, and 98 mil. So then motor casings are also generally sold in that size range. So you'll have like 2-inch, 3-inch, 4-inch, and 5-inch, roughly in between. So those are how the aft airframe works. Fins are held in place through the wall and with centering rings. So centering rings are essentially ways of containing the motor tube. They are spacers that ensure that the aft of the rocket maintains concentricity. It maintains circularity within the rocket. So if you look at the aft of the rocket, it's like a long cylindrical tube. This motor tube, the only way it's going to be able to stay like perfectly in place is with these centering rings. The centering rings are what's going to hold it in place. Yeah, concentric. Words are tough. So generally there are like the rule of thumb is you have 3 centering rings. You have one at the front to hold the front end, and then one in the middle and one at the aft. The 2 aft ones are the most important ones because they're also used to help hold the fins level. So these fins, if you see them, they protrude all the way from the top of the center ring to the bottom of it. So this mounting technique is called through the wall airframe or through the wall fins. So you mount it through the wall of the rocket to the base of the motor tube. These are the most secure way of holding centering rings or of holding fins on a rocket. And then generally when you're manufacturing, each of these components are going to be epoxied in place. I'll talk about rivets and shear pins later on. Okay, I don't like this quiz. We're not doing quizzes. So on a rocket, you have several components, right? On the outside of a rocket, you have your airframe. Airframe is what contains all of the essential parts of a rocket. It'll contain your avionics and recovery, your parachutes, your shock cord, and your payload. So the way that we do airframes is that we purchase them commercially off the shelf. So you can call that COTS, right? COTS, commercially off the shelf. Since we're buying them commercially off the shelf, we buy them from special retailers. So we buy them from like just specialty rocketry retailers. And when they sell them, they'll generally make them out of these materials here. So you have cardboard, quantum tube, phenolic, blue tube, fiberglass, and carbon fiber. The team, when we generally make our rockets, we prefer to make them out of fiberglass. Fiberglass is probably the cheapest and strongest material that we can make them out of. Carbon fiber is obviously ideal, but carbon fiber is expensive. We've only been exploring carbon fiber as of recently because Gavin is researching them as part of his project. Blue tube is a very beginner airframe material. So blue tube, phenolic, and quantum tube, those are generally what are made for L1 rockets. So these are weaker materials. They're more prone to warping, water damage, but they are very reliable for low rockets. So inherently though, all of these materials are more than strong enough to launch a level 2 and level 3 rocket. But what becomes a concern is when you launch rockets over and over again, they're going to become prone to damage and warping. So if you see here, like blue tube is made out of essentially paper that's been wrapped and mixed with epoxy. Same with phenolic. Phenolic is also some kind of cardboard wrapping. Quantum tubing is a plastic. An issue that we had in our past is with blue tube and quantum tubing, our blue tube and phenolic, is we had water damage as an issue. So when you're designing a rocket, these materials, there's something to consider between why you're choosing which one. Carbon fiber, really strong, really light, extremely expensive. Fiberglass, significantly cheaper, but a lot heavier than carbon fiber, but is also very strong material. So these are just things to consider. So if you're thinking about like damage or health concerns, all of these pose an inherent health concern when you're manufacturing. Manufacturing is, there'll always be a concern of like when you're making it, you'll get dust from like cutting it or like the epoxy, the fumes. So like generally you want to avoid it. You wear a mask. We do have respirators, but we're still working on trying to get respirators rolled out to everybody. Recently, they cracked down on them because when you wear a respirator, it restricts your airflow. So there was an incident a few years ago. So you need to get like tested to use a respirator. But in the meantime, I do believe we used to have N95 masks. Those are generally good enough to stop the particulates that come out when you're cutting these dusts. So those are airframes. You have nose cones. Nose cones are pretty important. They go on the tip of your rocket, reduce drag, right? So this is a rocket from FSU. This specific design is because they were launching, I believe, a camera that they want to point it up at the sky. So while it does look kind of stupid, it is like reasonable to consider that when you're launching at a lower speed, the general shape of a nose cone doesn't matter too much. If you remember from the flight dynamics meeting last week, like how pointy a rocket is doesn't matter too much at lower speeds, because when the air is coming in through it, it doesn't need to push away as much like air. So it being blunted on the front doesn't really matter too much. But at higher speeds, yeah, you'll want like a really nice nose cone. Metal tip really doesn't matter because you're not going fast enough that it's going to heat up. So it's really just for looks. And then just to make it look cool, it also helps stability a little bit because it moves the center of gravity forward. So those are your nose cones. Nose cones, they are generally made in this shape. You have different shapes that I talked about last week, but when you buy them for lower powered rockets, they'll generally be sold as one entire piece, while when you buy 4 or 5 inch rockets, they'll be sold as 2 pieces. 2 pieces being the actual shape of the nose cone, and then this coupler piece will be detachable. So that's just a design consideration when you are buying these components. So you have your fins. Last week we talked about the importance of fins and their shapes. So we're just going to talk about the different manufacturing techniques available to us to make fins in our desired shape, and then the purpose of them. So generally fins are made in sets of 3 or 4. 3 is generally the best way to go because 4, when you go to 4, the increase in drag and CP, it's really a balance of what kind of design you have. So like if you have 3 fins, they'll generally be very large. If you have 4 fins, they'll be smaller. So it's like a consideration of, do you want to have an increase of mass from 4 fins or 3 fins that are larger? It's like a balance of designing an open rocket. So there are a few materials you can make fins out of. The team normally uses G10 fiberglass. So there are like 2 different types of fiberglass. There's the fiberglass for these sheets, and then there's also the fiberglass for these airframes. So these are G12, while sheets are made of G10. So the difference between these 2 types of fiberglass is that G10 is in sheets. So you have sheets on sheets and like little layers of laminate, and in between them you put epoxy. The way that G12 fiberglass works is that it's filament wound. So you'll have essentially a long strand of string, and then it'll wrap around a mandrel. So that's how you get a tubular shape. That's also how carbon fiber is made, except with both carbon fiber and fiberglass, instead of like winding it, what you can buy are called sleeves. So it's a pre-wound sleeve of fiberglass, and then when you put epoxy on it, it'll contract and harden. So I believe you guys are nodding. So I'm assuming Gavin's been doing that with carbon fiber. So that's just different manufacturing techniques between G12 and G10. There's also another type of fiberglass that we use, which is called structural FRP. I believe it stands for structural fiberglass resin composite. So that's also just a different type of filament with epoxy. If you go on McMaster-Carr, you can see specifically like what kind of components that we buy for these materials. So on McMaster-Carr, you can see like, oh, here's G10, here's structural FRP. At the same like thickness, 1/8 inch thickness, you can see that you can compare the differences between tensile strength, compressive strength, or like hardness. So then from there, that's what you'll be able to decide, okay, I really like having fiberglass or G10 fiberglass as opposed to structural FRP because it's stronger, it's lighter, and then like it has these different properties. So it's all about doing research on these types of materials for your desired like outcome. So fin attachment, talked a little bit about it before. You can see a better picture here. You have your fins through the wall of the airframe. So on your fin, you have different components. I believe from tip to tip, that's your cord. This specific part that goes into the rocket, we call that a tab. And then on the outside of the rocket, you have your different like parameters, which you can play with an open rocket. So the ideal way of mounting these fins are obviously through the wall. Through the wall is the preferred way because you have 3 points of contact. You have a point of contact right here between the motor tube and the fin. So that's one. You have one on the exterior here. You have one on the interior of the rocket, but on the top part. So that's two. And you want to have one on the exterior of the rocket. That's three. So you have 1, 2, and 3. That's 3 points of contact of holding this entire fin into the rocket. So if you're thinking about ways that this can fail, is that when your rocket is falling to the ground, the fins will almost guaranteed be the first part that makes contact with the ground. That's where it's going to be impacted. So you probably have like a 40-pound rocket traveling at 30 feet per second, hitting the ground. So what's going to fail isn't necessarily this epoxy bead that you're putting here. It's going to be the fin bending. So that's probably more ideal than the rocket breaking right here into the airframe, because that'll be the weaker point of like this connection. It's going to be the fin material as opposed to like the airframe or the motor tube. Alternative methods of attaching a fin to the rocket is surface mounted fins. So instead of having this fin tab through the wall and then having a spin slot into your motor, into your airframe, you're just going to have like a little bead on the exterior of the rocket that is going to epoxy it. So if you think about it like on my camera, you're just essentially just gluing it like this. And then you're just gonna have to trust that it's like perfectly straight level and then it won't come off. So adhesives versus mechanical. If you're familiar with the IREC rocket, IREC is doing a mechanical mounting method of their fins. That's very experimental, so I will not talk about it. Chances are you won't do that as your L1 since there's a lot of machining and then it'll be very heavy. But as an overview, what they're doing is essentially replacing all this epoxy with mechanical fasteners and just different brackets so that it becomes modular. So modularity is a big advantage because it means that if something breaks or you want to change your design, you can change it. With epoxy, the moment you lather it in epoxy and it cures, you're stuck with what you have. And there's pretty much no easy way of changing your design, or something goes wrong, you're going to have to rebuild it from scratch. Couplers. So for a level 1 rocket, you probably will not need a coupler, but couplers are very useful for level 2 rockets and also are the rockets that we normally launch. The way that it works is you have a large tube and a slightly smaller tube that when they slide into each other, they fit perfectly together. Ideally, there's not a lot of give, because when there's give, that means the rocket can vibrate, and you have two separate pieces which are going to be torquing and vibrating and oscillating between each other. So if you go to the top here, couplers are essentially what holds together these pieces, these brakes in the rocket. A coupler is a standard size of probably like 0.1 inches smaller, and it goes roughly from one end to the other end of the rocket to make sure that it's held in place. The rule of thumb, not even a rule of thumb, the rule for using couplers are that the shoulder length of a coupler, which is from here to here, is about 2 times the diameter of the coupler. So if we think about the coupler being 3 inches in diameter, so the tube is 3 inches from like here to here, this shoulder will need to be, hold on, am I messing up my numbers? I don't think it's 2 because it's obviously not 2 on the picture. I think it's 1. Let's just say it's 1. It says that on their website. Okay, so rule of thumb now, 1 shoulder length in, or 1 diameter length in shoulder. So if the rocket is 3 inches in diameter, shoulder will also need to be 3 inches in diameter. So yeah, if you can see it here, yeah, it's roughly 1 to 1. So then this picture also shows another component on this coupler. So the coupler is a small piece. There's a little segment right here in the middle. We call that a switch band. A switch band is essentially a piece of airframe that is epoxy to the inside of the coupler. The purpose of a switch band is that it helps separate the two ends of the rocket. So if you have a rocket piece on the top here and the bottom here, this middle piece will always be in the middle. So when you slide it on top of each other, there's no guessing of how far in they're going because they're matching at the switch band piece. So this entire coupler piece though as a whole is 1 diameter, 2 diameters, plus however big the switch band is. So if you have like a 3-inch rocket, your couplers are generally going to be 7 inches or longer. They are normally not smaller because these switch bands will feature avionics, things that are needed for your avionics recovery. Avionics recovery things that will be on it include buttons, key lock switches, and pressure port holes. Okay, chat. Shoulder is the white part. Oh, I am using my mouse. Okay, yeah, so the coupler is the white part on that bottom right picture. So when you do have a coupler though, it is pretty loose fitting, so you can rotate it. The way that you stop it from rotating is that you use shear pins and rivets. So you can see that up here, back earlier. So shear pins, as the name implies, are meant to shear. So if you can see the picture, they are essentially very tiny nylon screws. These screws are meant to break. They are designed with the purpose of shearing in half. And when I mean shear is that if you have like a pair of scissors, imagine your coupler and your airframe as that pair of scissors. So you have one end and then the inside end, and then they'll separate and it'll rip it in half or it'll cut it in half. So that's what a shear pin is made to do. Rivets are meant to not break. So they are made out of a thicker material and a lot stronger. So the difference between shear pins and rivets is when you have your rocket, you want rivets to not break, shear pins to break. So like, how is that useful? Shear pins, when you put them in your rocket, they will break instead of rivets. So if you pressurize this entire little piece of airframe and you put rivets on one end, shear pins on the other, the side with shear pins will fly off. So if you have rivets on, let's say we have rivets on this middle piece, right? The one with the fins in the middle, and then you put shear pins on the part above it. These rivets and shear pins are going to drill through the airframe into the coupler. So they're going to go through both of these pieces here. And then you pressurize it using an ejection charge with black powder. The side with the rivets will hold in place while the shear pins will fly off. So if you have rivets on the middle piece here, shear pins on the top half, when you deploy your E-charge, the top half will fly off while the bottom half will stay intact because of your choice in between shear pins and rivets. So then what you can do with that information is that, say you want one end to deploy sooner than the other, you'll do maybe rivets on one end, shear pins on the other, so that your drogue parachute or your main parachute or your payload, whichever way you decide to deploy them, it'll launch in the desired order. And they talk about it again here. Here's a better picture. So nylon shear pins, there's no general size to them, and there's not like any specific way that we do math with them in terms of you need this amount of force. It's very guess and check. If you saw it today, Brita from testing, she did ejection charge testing. So she's specifically working only with shear pins and rivets to like deploy those specific components. So that'd be a good video to look at. Okay, slide. There's, yeah, next slide. So bulkheads. Bulkheads go on your avionics bays. A bulkhead is a way of separating the interior of the rocket into two components. So you'll have the one component on the exterior and then what's contained within the bulkhead. So bulkheads go on either end of your couplers, and when you stick two bulkheads on either end, you essentially have an avionics bay or just a bay. Bulkheads are being featured on the SL rocket to separate the avionics bay and also to separate the payloads bay. So this is a very like generic bulkhead with the components on it. We don't really use this design too much anymore because this bulkhead features charge wells. So charge wells are a way of containing ejection charge gases or of your black powder. We don't really do that anymore. What we prefer using are floating wells or floating e-charges. There's really no like benefit to using one over the other than charge wells. They will always be like located on the bulkhead and they direct the blast upwards, while floating charges, they have more modularity or they're more accessible so that you can move them like wherever you want. You can put them like on the opposite end of where this is, and you're not restricted by the location of them. What else is on this bulkhead are eye bolt. Eye bolts are used for your avionics and recovery. That's how you do shock ward. You have terminals. Terminals are used to connect to these charge wells. And then these are threaded rods for your avionics recovery. I'm not going to talk about that stuff. I'll leave that to Bryce next week. So how are they held in place? They are held in place with these threaded rods. So there's one here. There should be a mirroring one right here. So if you remember with the couplers, the coupler slide, the coupler has one end at the top, one end at the bottom. You'll have bulkheads sandwiching it. So you'll have one bulkhead on top, one bulkhead on the bottom. The specific design of a bulkhead, you don't see it on this one, but they're generally made with a shoulder built into them. So the bulkhead, it'll be made so that it can slide on top of the coupler, but not go through it. And then when you have two of them on either ends and you connect them with threaded rods, the threaded rods will essentially sandwich them together so they'll be compressed. So that's how they're going to be held in place. Okay. Okay, you can see the shoulder here. So like this part will go into the coupler while this part right here will be the minimum diameter. So it'll be able to fit in the airframe, but not go through the coupler. Then this part will go through the coupler. So materials that bulkheads can be made out of, if you go back to fins, they can pretty much be made out of the same exact material. You can make them out of fiberglass. SL this year made them, or IREC made them, SL made them out of type 2 PVC, which is some kind of plastic. In the past, we've made them out of plywood. There's really no like winning design of what you make them out of. Okay. Yeah, you can see them here. And then bulkheads, the way that they are manufactured, same with fins, are you can make them on the water jet. You can make them on drill press as well. There's a tool that makes them out of perfect circles. So there's different ways of manufacturing. Thrust plate. So on your rocket, the motor will go on the aft of the rocket. And then should we remember this design, you have 3 centering rings. So the aftmost centering ring will also act as a placement for the thrust plate. So the way the thrust plate works, it's very similar to the design of a bulkhead because it has a shoulder on it. So when the rocket deploys, the motor is going to put all of the pressure onto this thrust plate. The thrust plate will then transfer the thrust to the airframe, not the centering rings. It goes straight to the airframe, because of the shoulder built into it, just like the bulkhead. You can see on the left picture. So when you deploy a rocket, the motor pushes on the thrust plate onto the airframe. What a secondary purpose of the thrust plate is that it also holds the motor in place. So when the motor is deploying, it's pushing upwards onto the rocket. And then once the motor is done deploying, it doesn't fall out of the rocket because it is being held in place by the thrust plate and also by the motor retainer. So if you see on the right picture, that is the motor retainer. That's a flanged motor retainer. It has a series of holes on it. Those holes go directly onto the thrust plate. So the motor retainer, it is pretty much not load bearing at all. It doesn't help the rocket during flight. It helps it after flight to prevent the motor from falling out of the rocket. So it doesn't necessarily need to be very strong. So these are like very over manufactured and extremely expensive. They're like $70, $80 for not being a terribly strong piece of material or needing to be a strong piece of material. And then we touched earlier on about motor tubes. Motor tubes don't need to be very strong. The only important feature of a motor tube is that it is perfectly cylindrical. So it just needs to maintain concentricity throughout the rocket. They don't need to be very heat resistant because motors, while they do get very hot, the heat is contained very well within the motor casing. So that's just some design considerations. So your motor tube doesn't need to be strong. It can't be very flimsy, but it just needs to be a really long straight piece of tubing. Centering rings. Okay, so kind of talked about it before. Centering rings, the main purpose is just to hold the motor tube in place. You will not be using these manufacturing techniques. The one at the top, that's for baby alpha rope motors. Those are like very rudimentary ways of maintaining a motor. Epoxy. So epoxy is pretty much how we get everything done on the team. If you want to make any kind of bond or make sure anything is held together, use epoxy. There are two types of epoxies that we use. We use JB Weld and we also use rock epoxy. The two main differences between JB Weld and rock epoxy is that JB Weld has I don't know the specific term, but it has a failure at heat of about 500 degrees Fahrenheit. Rock epoxy will fail at, I believe, around 300 degrees Fahrenheit. So generally what we would do is when we're epoxying the centering rings and the fins, we would use rock epoxy on the interior of these epoxy beads because it has a higher like heat capacity. Not heat capacity is not the right word. It has a higher it can withstand higher temperatures before failing. Rock epoxy, on the other hand, while it can only withstand to, I think, around 300 degrees Fahrenheit, it is significantly stronger than JB Weld. So we will use JB Weld pretty much everywhere else. JB Weld is a very nice epoxy. When it cures glass-like and very smooth. So it's very desirable to have rock epoxy on the exterior of the rocket. If you see here on the carbon fiber, it makes a very nice fillet on the exterior of your rocket. If you use JB Weld, it'll be a little bit more clumpy and it won't spread as nicely. Some other stuff we use is 5-minute epoxy, but we mainly use 5-minute so that it holds it in place until we can use either JB Weld or rock epoxy. So we would use 5-minute epoxy when we're doing fins so that the fins don't shift while the really nice epoxy is curing. So that is the structures meeting. So these are the materials and different I guess didn't talk about manufacturing techniques, but these are different materials that you can choose to design your rocket. So pull up Open Rocket. Okay, share screen. Okay, so here's my own personal rocket that I've been designing. The way that you would use materials here is that the Open Rocket pretty much knows what kind of material you're going to use since they are all very specialty. So for example, the nose cone, they're probably going to be made out of plastic. So plastic is polystyrene. airframes, you can do the same exact thing. Materials, so you have quantum tubing, wood, steel. You probably do not want to make it out of steel. Like steel is extremely heavy, overkill, and also they don't let you launch rockets made out of steel. It's a hazard. So regardless, steel is never going to be an option. And then you have other things here too. So when you're designing your rocket and open rocket, you can play between all of these materials. And then if you go back to the PowerPoint, the materials that these are generally made out of are going to be your quantum tubing, phenolic, or blue tube. Those are the cheapest alternatives to fiberglass. There is no like win all for airframes. It just depends on whichever one you want to choose. Like blue tube is pretty light, quantum tube is pretty flexible. I don't like phenolic, but you can just choose between these materials. Like if you go on Apogee Rockets, that is our main vendor. Yeah.
Why did SL use Bluetooth last year?
Okay, so blue tube last year, that was when I was the structures lead last year. We had pretty heavy money issues last year because that was pretty much, we were in the thick of COVID. So we were being threatened with not having funding for the team. So the issue with that is like, how are we gonna pay for all of our components if we don't have money? Blue tube is very, very cheap compared to fiberglass. We prefer blue tube to phenolic because they don't make phenolic at the sizes that we wanted. So I'm pretty sure they don't make 4-inch, they don't make 5-inch phenolic. So when we're doing our subscale rocket, we wanted to use the same material for both of them. So that would lead us to blue tube. Quantum tubing, we don't really like using quantum tubing. Like it's great, it's really strong, but we've never used it on a big rocket. We have used blue tube before on big rockets. So we had experience with it, we know it works. An issue that we had though with blue tube is that it either landed in water or I think it was just very humid out. So what happened is that blue tube is made out of cardboard, so it absorbed water, and then when it absorbs water, it contracts and then it no longer fits like it used to. So I think we had issues with our couplers not fitting, and then we eventually had issues with leaking. Okay, so if you're curious what our vendors are, we have Apogee Rockets. So when you're choosing your design, you can't just design it however you want it, whatever looks coolest. You have to design it according to what is available because you will most likely be like purchasing these commercial off the shelf. So the airframe. Yeah, so here's blue tube, like 2.56 inches. And then here's your thickness. Here's your inner diameter, outer diameter. So your design can account for all of these like different parameters, and you just need to make sure that you're designing it such that what you're designing is manufacturable and can also be purchased. And same with fins. So these fins, they're made out of fiberglass. I think density is off. So what we can go is we can go to Master Car. You take DML, Master Car will be your best friend. It's honestly a great website. Like if you ever need any kind of component, it is already pre-CADed for you. So all you have to do is download it, and like if you need like a nut or a screw, it's already pre-made for you. It's great. So then here's the fiberglass I was talking about. We have structural FRP fiberglass, and then we have Garolite G10. So while there's nothing wrong inherently with either one of them is significantly better. So G10 fiberglass, if you look at it here, tensile strength of 35 to 50,000 PSI, impact strength of 5.5 to 12. We compare that to structural FRP, tensile strength 7 to 30,000, 7 to 30, compare that to 35 to 50, right? Impact strength 4 to 25 compared to 5.5 to 12. So there are trade-offs between both of these, and then you can also compare prices, right? 1/8 inch stick for a foot by a foot compared to 1/8 inch by foot by foot, $24 versus 16. So there are just these different design to consider when you are designing and manufacturing, so that these are the things that you'll do when you're making your design reports for SL or IREF. You have to make these design decisions, say, okay, we have a budget of $4,000, right? Sure, we can choose like the nicest materials, but is it really the best material? Do we actually need 50,000 PSI of tensile strength, or is 8,000 PSI tensile strength good, right? So just different conditions you need to consider. And then your motor tube, again, motor tube doesn't matter too much. Same with your centering rings. So another thing to consider is manufacturability. So when you buy your components off of McMaster-Carr or Apogee, you have to consider how long and how big everything is. So you have 48 inches, your sheets, you can buy different sizes. So like here, your biggest coupler length is 48 inches. I'll find airframe, but your biggest airframe is also going to be 48 inches. So that means you can't have a rocket component that is 50 inches because you're never going to be able to get it 50 inches because the longest they sell is 48 inches. And then just other design considerations is if your diameter are not exact, it can make a very big difference on the weight of your rocket. Because if it's like 0.2 inches, that's 0.2 inches throughout the entire rocket. That's going to be a sizable amount of mass. And then your apogee is off and your stability is off. And now your open rocket is kind of useless because of that small little error that you didn't check when you're designing it. So design manufacturing that you're going to need is there's really only going to be 2 or 3 machines you're going to need to use and manufacture. Those cones, when you buy them, they're exactly ready for you. Airframes, you'll have to cut them down to size. You're going to do that on a bandsaw, on a Roland bandsaw, right? You just cut them smaller. Bulkheads, you can make them either on a water jet, depending on if you're using sheets, or you can make them on a lathe if you're using something like type 2 PVC. And then with your fins, you can either cut them on the bandsaw if you hate yourself, or you can do them on a water jet. I say that because my first 2 years as lead, we cut them on bandsaws. What we would do is we would print out the piece of paper on 1-to-1, trace it out onto our piece of paper, onto the sheet, and then cut them on bandsaw. So they were roughly the same. Yeah. So that was before we had like 5 DMLTAs on the team. And then centering rings, you're going to want to make those on the water jet. The way that we made them in the past is we used the drill press. Let's see if I can find the tool. We used the drill press and then we used the circle cutting tool and we pushed it down into the piece. The thing that's wrong with the way we did it is that this is a wood cutting tool and we used it on fiberglass. So when you're cutting fiberglass with a piece of metal, that's not meant to be cut like that. It made a lot of smoke. Pretty much made the entire STC like thick with smoke, and then it just smells awful because you're burning it off. So that's different designing techniques. Yeah. Like, yeah. And then other things to think about are you have your, where's the slides? On the bulkheads, where the bulkheads. You'll need to think about like designing the bulkheads, right? They'll need holes. If you're not using chargeables, you need to think about what are your floating, well, your floating ejector charge is going to be made out of. You're going to need to think about like ports to hold these terminals. Don't forget about wiring. We've kind of about wiring before too. So you're going to have to like drill wiring holes, which is what this one here is. And then different materials for your threaded rods. We'll talk specifically about the design of like bulkheads for your avionics recovery next week, because next week is avionics and recovery. And then there's other stuff to think about too. So on this rocket, there are also like rail buttons. Rail buttons are how you launch a rocket into the sky. Rail buttons will guide the rocket off of a rail so that it maintains level flight until it achieves a desired velocity and stability. If it doesn't have the rail buttons, there's nothing telling the rocket to go straight up when it deploys, and then that'll cause a pretty catastrophic flight. Okay, so that's about it. I did not intend to go into open rocket, or I don't really intend on talking anymore about open rocket. Main purpose of this was to tell about different materials and design choices of these materials. Specific manufacturing, I think probably just save that for a future meeting where you guys will design it, and then we'll look at the design and say, okay, this is manufacturable, this is not, this is why. So yes, homework that your homework has always been is just keep playing with your open rocket, like get more comfortable with it. Choose materials that you can find on Apogee. Apogee is not the only website. There's also Mad Cow. Mad Cow is unreliable. We ordered a nose cone from the second week of January, still has not come in yet. So there's this place, there's CS Rocketry. They sell other components. What else do I have? Yeah, so there's just different vendors where you can buy all these things from. I believe it's somewhere on the OneNote that all these vendors are listed, but yeah, since we're buying everything COTS, you want to design your rocket as a COTS rocket. Okay, so that's about it. You guys have any questions about anything? No? Okay, so next week will be avionics recovery. I think that'll be hosted by Bryce. We'll talk about parachutes, shock cords, and then deployment methods of those things. All right, so thanks for coming to this meeting, guys. I will post slides, post a recording, and then I'll see you next week. See ya.
It's like